Think of any number from 1 to 100. Got one in your head? Don't tell me. Now watch. I'm going to find it. Here's every number, 1 to 100. Your number's hiding somewhere in here. Let's see. Is your number bigger than 50? There we go. So everything from 1 to 50, gone. That's half the numbers, in a single question. Now, is it bigger than 75? So it's hiding somewhere between 51 and 75. Half gone again. Bigger than 63? 69? 72? Bigger than 74? And now it's down to just 73 or 74. So, is it bigger than 73? And that leaves exactly one number, 73. So how did I corner your number so fast? Simple. Every single question, I threw away half of everything still left. That is the core idea of binary search. Check the middle, throw away half. But there is one catch. This only works when the data is sorted. Let's see why. Back in the game, asking bigger or smaller worked for one reason. The numbers were in order. Watch what happens when they're not. Now, if I check the middle, it tells me nothing. The number I'm after could be off to the left or the right. There's no way to know which. But put them back in order. And every check splits the list cleanly. Smaller on the left, bigger on the right. That's the real reason we go to all the trouble of sorting. All right, let's pin down the actual problem. You're handed an array of numbers, already sorted, smallest to largest, and a target, let's just call it X. The job, find where X sits in the array, or report that it isn't there at all. Here's the real code. We'll run it slowly, using the same number from the game, 73. We start with 2 markers. Low sits at the first index, 0. High sits at the last one, 9. Right now, the whole array is still in play. The loop keeps going as long as low hasn't passed high. That equals sign matters. When they land on the same spot, there's still one cell left to check. Next, we pick the middle. Read this as, start at low, then move halfway toward high. Here, that lands on index 4. Now we check the value at mid. A-mid is 25. Is that our target? Nope. 25 is smaller than 73, so the target has to be off to the right. So we move low to mid plus 1, and the whole left half drops away. Why plus 1? Because mid itself already failed the check. If the middle had been too big, we'd do the same thing on the other side. Move high left of mid. Now we repeat with the smaller range. The new middle is index 7. This time, a mid is 73. That's exactly X. So the answer is index 7. Return it, and we're done. And if the markers ever cross, the range is empty. Nothing left to check. That's when the function returns -1. So why is it this fast? Let's count the steps exactly. Look at how much is left to search after each step. At the start, all n items are in play. The first check throws away half, so n over 2 are left. The second check halves what's left again, n over 4. The third check, down to n over 8. And we keep going like that, halving, until just a single item is left. So the whole question is just this. How many times can we have n before we get down to 1? After k halvings, n over 2 to the k items remain, and we stop the moment that drops to 1. Multiply both sides through, and 2 to the k equals n. And the k that solves that is, by definition, the log, base 2 of n. So binary search runs in about log n steps. And that's the whole beauty of it. Double the data and you pay just one more step. 1 million items? About 20. So here's the whole thing in 3 steps. Check the middle, throw away half, and repeat. It only works on sorted data, but when the data's sorted, you can find anything in about log n steps, 1 million items in around 20. A simple idea with a huge payoff.